are going to find here. So now what I'm going to tell you, so when I have points like this, so if I have a two-dimensional space, I will try to come out with one function. So if the moment you assume you have a kind of linear separability, understood, so you can think of a line like this. So you have, for example, you must have seen even in your +1 or +2, the equation of a straight line. So the equation of a straight line can be taken as y is equal to beta naught plus beta 1x. Understood? So I will, in other words, I'll put it like this: beta naught plus beta 1x1 or beta 1x some minus y is equal to 0. So I will plot this line. So the two-dimensional version of the hyperplane happens to be a straight line. So I'll try to find this line. So what I'm going to do now, I have here some points here and some points here. So I'm going to use the value taken by this particular function. If you want, you can call this as x2 and x1 also. No, it hardly matters. Now, this beta 1 and beta 1 are going to decide the characteristic of your straight line. So this is going to be intercept, and beta 1 is going to be your slope. So what I will be doing, so when I have a two-dimensional space, I'll try to find one line which will help me to separate the positive points and the negative points to the greatest possible extent. Understood? So what I am saying, the moment you assume we have linear separability, understood? So here I have a set of points here and I have a set of points here. So when you have linear separability, I am saying you'll be able to draw one line which will be able to separate the positive points and the negative points. I hope you can understand. So the problem here is, the moment you have linear separability, you will not get just one line. You will get one line like this, one line like this, one line like this. So you have plenty of possible straight lines which will separate the positive points and the negative points. So what we have to do now, we have to find one particular line which will give us the best amount of classification. So towards that, what do I do now? I go for two quantities called d plus and d minus. So d plus and d minus are two quantities which I will use for measuring the level of or measuring the amount of separation we have between the positive and the negative points. That is what I have explained here. So here, what we will be doing now, we will be taking d plus as the perpendicular distance from the nearest positive point from the straight line. And similarly, d minus is the perpendicular distance from the hyperplane to the nearest negative point. So these two distances we can get, and those two distances can be added to define what is known as the margin of separation. So this is what we will be trying to do. Now we can get the value of this d plus plus d minus. We can easily show that to be something like this. Now what I am saying now, instead of having just two features, like we have beta 1 x1 plus beta 2 x2 etc. Beta or xr is equal to 0. I am saying the margin of separation we can get by adding d plus with the d minus. With a little bit of algebra, you will be able to get this distance as 2 divided by norm beta. Now it was told earlier, I would have taken yesterday's morning class and I could have done it in a more leisurely manner. Understood? So if you wish, I can send these presentations for your course, provided you assure me that you will not misuse it. So here we have some simple, it is not high-level mathematics, it's only a +2 level mathematics, which will help me to get the margin of separation 2 divided by norm beta. Understood? So when we have linear separability, the difference, in other words, the margin of separation created by a hyperplane is given by 2 divided by norm beta. You can ask me what is that norm beta. Norm beta is nothing but square root of beta 1 square plus beta 2 square etc. beta p square. Probably you must be beta r square. It is your L2 norm, which we normally use for the purpose of regularization even in the LPA also. Understood? So even if you have not understood anything, just you listen to the statement which I am going to make. Understood? So what I am going to do now, when I have x1, x2, etc. xr, when I have x1, x2, etc. xr, all features, understood? When we want to perform classification, I have only one plus class and the minus class. So what I am going to do now, I am going to make use of the training data set, and I would like to construct this plane beta naught plus beta transpose X. That's what I'm, or in other words, we can have beta 1 X also, because suddenly there is a shift. Okay, I'll take this as beta 1 X. Okay, now it goes like that. So, right, now what I'm trying to tell you now the question is, how, so I would like to get this one. Now, what is this X? X is the training data set. I'm going to use this to decide the membership for a particular training object. So if it takes a value greater than or equal to 1, I'll put it in the positive class, less than or equal to 1, minus 1. Okay, so it is there. But what is not known here? Madam, Mandana madam, can you tell me what is not known here? Can you tell or not? Say yes or no.
X value known value.
So this X vector is fully known. So this X is fully known. What is not known? Beta naught and beta 1 are not known. Am I correct? So if you see, for example, if I tell 2 plus 3x1 minus 4x2 plus 5x4 plus 5x3 minus 6x4, if I give a function like this, I am saying you do not have any unknown value, because this x1, x2, x3, x4 values are values assumed by the features in the training data set. So whatever values I have here, I will substitute and I will see whether it is greater than or equal to 1 or less than or equal to minus 1, and I will put it in either in the positive class or negative class. Okay, so you can do like this, provided you know what is this 2. I am saying this 2 is something like your beta 1. This beta 1 is a vector consisting of a 3, minus 4, 5, minus 6. So all those values will come. So basically, this hyperplane is known as hyperplane, which is going to help us to perform what is known as classification. So ultimately, we want to find only beta naught and beta 1. So that is our main target in the case of your support determinations. So how we want to get beta naught and beta 1? See, we will be getting beta naught and beta 1. So we will be getting beta naught and beta 1 by maximizing the margin of separation. So for want of time, I'm not going to stick to that. So the margin of separation is given by 2 divided by norm beta 1. So this is the margin of separation. This we can easily get. It is a very small one. Then, so we would like to maximize this margin of separation. I am saying maximization of this is equivalent to the minimization of norm beta 1 divided by 2. Understood? So instead of maximizing f of x, so if maximizing f of x is equivalent to minimizing your f of x. So this conversion will be doing. You will know why I do this a little later. Understood? So I will be focusing on finding I will be focusing on maximizing the margin of separation. That means I would like to find beta 1 so that this is maximum. That is equivalent to finding beta 1 so that this is minimum. This is same as minimizing norm beta 1 square divided by 2. Because remember, minimizing f is equivalent to minimizing your f square. And also when I square this, I am getting 4, so that the constant will not have any effect at the time of optimization. So basically, this beta naught and beta 1 are obtained by this process. So you minimize this norm beta, half of a norm beta 1 square, subject to the condition. The conditions happens to be this beta naught plus beta 1 x greater than or equal to 1 for all points which are in the positive class. Understood? For all points which are in the negative class, we'll be having this one. So this is basically a convex optimization problem. That means here it is a quadratic function, quadratic form. Understood? So you maximize this function subject to this one. For this, we can use any quadratic programming technique, and you can come out with a solution. And once you have your beta 1, you'll be able to get your beta naught. Understood? So now I am saying, so here I have given some examples which I used to give for our students. So basically, just I'll summarize what I have done. So I am saying, in support determination, the separating hyperplane is obtained by maximizing the margin of separation. So the margin of separation is basically 2 divided by norm beta. Maximizing 2 divided by norm beta, I am saying, is equivalent to minimizing half of a norm beta square. Understood? So we minimize this function function, not without any constraint. Because when you don't put any constraint, I don't want to tell stories because we are not having much time. So see, if you try to do some unconstrained optimization, you'll be getting a globally optimum solution which will be trivial. Understood? So that means if you try to minimize this, you can give norm beta equal to 0. You can make it as 0. So you will not get anything better than that one. So half norm beta square is a positive quantity, non-negative quantity. If you want to minimize this one, it looks like the best solution can be beta equal to 0. But it is not like that. So you have to put some constraint. What you are going to do with beta 1 equal to 0? You will not have any hyperplane at all. So this problem can be solved. All those things we use to illustrate in our regular classes. Okay, so this is what I wanted to tell. Okay, so everything works well as long as you have linear separability. Everything will work out very well as long as you have linear separability. Now, once again, I will repeat. I would like to repeat. We want to find this function. We want to find beta naught plus beta 1x. Beta naught is a scalar. It is a constant. And beta 1 is a vector. And x is also a vector. Now this is 1 cross 1. Beta 1 is 1 cross r. X is r cross 1. I hope you can understand. Because I have r training features, x1, x2, etc. xr. So this is the function which you want to use. So this is your equation of your hyperplane. I said we are going to find beta naught and beta 1 so that this hyperplane will help you to achieve maximum separation. So the maximum separation is defined by 2 divided by norm beta 1. This we can get in no time. It will not take more than 10 minutes, but even for me, the 10 minutes also matters. So you would like to maximize this. How do I maximize this? I intend to use this plane so that beta naught plus beta 1x is greater than or equal to 1 for every positive point, for all x in the positive class. Understood? So beta naught plus beta 1x will be less than or equal to -1 for all x in the negative class. So this is what we are going to do. Now I am saying you can convert this maximization problem into a minimization problem like this. Norm beta 1 square divided by 2. So you get beta 1 by minimizing this one subject to this condition. So we have a lot of quadratic programming methods, like we have a method called Wild's method, or we have a method, if you want, you can use. Those who have studied optimization, non-linear optimization will understand this one, but for you, for a data scientist, it is not at all necessary. So so you can solve this and you can come up with the answer, and once you get that beta 1, you'll be able to get beta naught directly. So it is a very, very long history. So okay, so now I am saying you have understood this solution will help us to get the support vector plane. Understood? In other words, the hyperplane. Okay, now that plane you can use only when you have what? Only when you have linear separability. When you do not have linear separability, then the problem becomes quite complicated. So what do we do now? We go for a kind of soft margin technique. So instead of having that half norm beta 1 square, here we'll be having some constants like this, some psi I into beta naught plus beta 1 xi plus minus epsilon I, something like that we'll be having. Understood? So we'll be introducing the concept of just let me check whether I have my screen, because if I, so I will show you better. So it is there. This is a presentation which contains the entire derivation. Understood? Just 1 minute. Not because I don't want to make things very vague. Understood? So I'll just come up to this. I do not know whether any participant is available there or all of them have run away, because it will be a threatening experience, no doubt about it. So, sometimes it happens, even resource persons, but rarely someone who studied under me behaving like this is something unacceptable for me. So here I have given the entire story. I said, so here we have the derivation for that margin of the separating hyperplane. Understood? So those inequalities, how they come also I have given. So once I have that, I'll be having with me my beta naught and beta 1. So that beta naught and beta, the by solving this system of equations. So the final solution happens to be this one. So your beta hat is going to be summation alpha I hat yi xi. So this xi is going to be the training data set value, and this yi happens to be the actual class in the training data set. This alpha I hat is a constant which will satisfy these equations. So here we will be having a set of equations like this. So here we have alpha transpose y equal to 0. So this is how we get our, I feel really sorry for talking like this, but I want one of you to summarize what then only it will make some sense. Can anyone of you summarize? Or totally everything is blank? I'll put it like this. This is my game. This is my game. I want to get some function of x, which is beta naught plus beta 1x. Am I right? This is my x. Aim. I want to find my beta naught plus beta 1x. Have you understood? This is my aim.
Okay.
One is talking. Say yes or no.
Yes, sir.
Who is talking? Vandana.
Yes, sir. Yes, sir.
Okay, madam. What are you going to do with this? See, I want to find this. Finding this means I want to find my beta naught and beta 1. I want to find my beta naught and beta 1. Beta naught is a constant and beta 1 is a vector. Okay, I want to find this hyperplane. Now, how do I want to make use of this hyperplane? What I will do now, I will substitute the training data set and I will see whether it is greater than or equal to 1 or minus 1. Understood? Accordingly, I am going to use that hyperplane for the purpose of the classification. Have you understood up to that? Say yes or no.
Yes, sir. Up to that understood.
Okay, so I am saying aim is this one. How we are going to use this? Understood? Find f of x value or f of x naught value, where x naught is a training data set point. If it is greater than or equal to 1, using this, you put that x naught into the positive class. If it is less than or equal to minus 1, put that x naught into minus class. So this is how I am planning to use that hyperplane. Okay. Now, how I am going to find this? So I am saying you find beta naught and beta 1, so that the margin of separation is maximum. So margin of separation is maximum. Why it has to be maximum, or that needs a lot of explanation. So I am saying the margin of separation is given by 2 divided by norm beta 1. Have you understood up to this? Margin of separation is 2 divided by norm beta 1. Please respond.
Yes, sir.
Yes. Or you want to know how that comes? How that 2 divided?
Clear.
Okay.
Clear, sir.
Yeah, so now I am saying you want to maximize this. I am saying you have to get beta naught and beta 1 so that it is maximum, subject to the condition that these two are satisfied. So for positive class, I would like to have beta naught plus beta 1 transpose beta 1 x greater than or equal to 1 for positive class, and for negative class it is less than or equal to minus 1. So I would like to maximize this subject to this one. I am saying that is equivalent to maximizing this, minimizing this. Maximizing that is equivalent to minimizing this subject to the same set of conditions. So this hyperplane beta naught, where I would like to find beta naught and beta 1 obtained by minimizing this quantity subject to the same set of constraints. Have you understood? Say yes or no. Yes?
Yes, sir. Yes, sir.
Okay. Now I am saying this, the solution for this problem comes via one intermediate step we have. We will be defining what is called a dual problem that I am not touching. Understood? Otherwise it will become quite unmanageable. So the solution for this beta 1 happens to be the solution for beta 1 happens to be some, I'll just put it here, understood? So then only we'll be able to follow. So the solution happens to be beta 1 hat is going to be some alpha I yi into xi. I am saying this is going to be a solution. So how many test objects we have? So some alpha I yi xi equal to 0. Understood? Now I am saying beta 1 you can get like this. Now you can ask me, what is this yi and what is this xi? See, this xi is the training data set corresponding to training value, training test value. See, I have xi means I'll have x1, x2, etc. xr. Corresponding to this, I'll be having a set of values. So those values will come here. Understood? And this yi, it happens to be either +1 or -1. Am I right? Say yes or no.
Yes, sir.
I think there is only one who is able to follow. Okay, so there is no problem related to this yi and xi. So these are known. But alpha I, all of a sudden it has come. I am saying this alpha I, with a little bit of a derivation, you can understand that alpha I is obtained by solving the system of equations. So I am saying, so alpha I you can get by solving this alpha transpose y is equal to 0. So you can get this alpha. See, that means what? We have alpha 1 y1 plus alpha 2 y2 plus etc. etc. Alpha yn is equal to 0. So remember y1, y2, etc. yn. What we have to do, we have to look at the solution of this equation for alpha 1, alpha 2, etc. alpha n. So this is how we are going to get our alpha values. So the moment we have the solution for alphas coming from this, and already you have from the training data set yi and xi value, you will be having your beta hat value quite comfortably. There should not be any big problem. Have you understood? Say yes or no? Yeah. Yes, madam. Any confusion?
No, sir, no.
Okay, it will be one very clear, understood. So the moment you have this one, you'll be able to get your beta hat value. So beta vector will come automatically. From beta vector, you can get a beta naught vector by this small summation. So this is a small work we have. So okay, so everything works well, provided you have linear separability. When you do not have linear separability, what is going to happen? So this is your optimal hyperplane. So the optimal hyperplane happens to be the solution you get here, this beta naught hat. So this beta naught hat which we get here will be, this is a constant, 1 divided by the number of support vectors. The number of support vectors means those sample points which will satisfy the equation of hyperplane either with +1 or -1 into this quantity. So we have completely determined the hyperplane. So here I have my beta naught hat and here I have a beta hat. So the entire thing comes like this. So the hyperplane happens to be this one. So this is going to be the most important part for me. F hat of x is going to be beta naught hat plus sigma I ranging from 1 to m. We are going to have alpha I hat yi into xi transpose xj. Here I have a scalar. Lot of mathematics is involved there. So this is my classifier. Now this classifier we can use only when we have linear separability. This classifier you can use only when we have linear separability. When we do not have linear separability, what do we do? When we do not have linear separability, what we have to do? See what we have to do now. See, if you look at this expression, the role of the training data points comes only here. This xi transpose xj. Here only you have the contribution from the features. So xi transpose xj is going to be this particular part. I think I this is one small mistake I have made. This is x transpose xj. Okay, so this is my training point. Okay, right. Now this x is going to be your test object, and you're going to get this one. Okay. Now this x transpose xj, this inner product is going to be the most important component of your hyperplane. Understood? So what we do now, we assume that when we do not have linear separability, I am saying we can achieve linear separability by projecting the points in the smaller dimensional space into a higher dimensional space, so that you can achieve linear separability. I'll repeat whatever I told you. Understood? So this is applicable only when we have linear separability. This we can use only when we have linear separability. I hope up to this we can understand. Can you follow?
Yes, sir.
Okay. Now, when we do not have linear separability, see, suppose you have a situation like this. I will show you a small smaller diagram here where I do not have linear separability. When I do not have linear separability, what will happen now? You will be having the points crossing over to other part. See, here these blue points represent my positive class, and these red points represent my negative class. Now what happens now? So some of those red points are getting along with those blue points, and some of your blue points go towards the red points. Have you understood? So these kind of situations are called inseparability, not the absence of a linear separability. So we do not have separability. So when we do not have separability, understood, what we do know, we can think of introducing a soft margin. Understood? So instead of having the constraint y into beta naught plus xi transpose beta greater than or equal to 1, I'll be adding on some psi I. Understood? So the amount of drift you have in the other region is indicated by your psi I. So those deviations will be summed, and we'll try to find beta naught plus beta 1, so that this margin of separation, which we are going to redefine here, I'm going to redefine here. So this is going to be half norm beta square plus c times sum of those inclusions. This I would like to minimize, subject to the condition this yi plus beta naught plus xi transpose beta plus psi I greater than or equal to 1. So this is how we'll be proceeding with this. Now the problem is, this is also not something which we can manage so easily. So the idea is this one: when we have the points in the smaller dimensional space, please listen. This is the more, even whether if you have not understood whatever I told earlier, if you do not understand this particular point, you will not know what is, how we fine tune the parameters in supported by classifier. Now suppose we have a two-dimensional space. I have some red points here, etc., and some blue points there. Understood? Total confusion is there. Now the points are not separated because I cannot create a separated hyperplane. What I am saying now, you can think of a three-dimensional or a four-dimensional space where every point in the two-dimensional space can be projected into the higher dimensional space. So when we project like that, some points will go there, some blue points will come here in the projected higher dimensional space, and some of them will come here. Okay, so it is a theory. So it cannot be easily proved. We have some mathematical properties. The thing is, if you do not have linear separability, in a smaller dimensional space, you can achieve linear separability by projecting the points. Projecting the points means what? For every point there, you create a representation in a higher dimensional space. There you will be able to achieve linear separability. So that is the main idea behind what I am going to introduce little later. Understood? So let me just tell you, I'll just show you a small video which will help you to have a very, not a very clear idea, some rough idea about these things. Okay, so this is one, probably I must have saved even in my system also. Just let me come out with that. Is it working? Well, am I audible? Why it's taking such a long time? Yeah. Yeah. Okay, so so this is one video. Now normally I used to show it to my students. So now you please listen. I have here, let me stop. Now you can see here I have a two-dimensional plot where the blue and the red points are not linearly separated. Some red points are getting along with the blue points. So the blue and the red points are not linearly separable. What I am going to do now, for these points, I'm going to create a three-dimensional space. I'm going to create, let me stop with this. Now you can see here, some red points are here and some blue points are there, some red points are there on the top. What I'm going to do now, I'm going to represent this, every point in this two-dimensional space will be represented in a three-dimensional space. Understood? So I'll be projecting these points in a higher dimensional space so that I can think of the separating hyperplane. Now let me move one step further. Now when I move like this, yeah, I get linear separability. Understood? So the point which I am trying to do is, if you don't have linear separability in the smaller dimension space, you can always think of, see, in fact, if you read those comments, you'll understand what type of transformations they have used for the creation of a higher dimension space. Understood? Probably some of you may be wondering why we have to give this idea. See, now please listen. Suppose I have points in a 2D. I have points in 2D. Here I have an x1 and here I have my x2. Now, for every point here will be represented as in a three-dimensional point. So suppose I have some x1, y1 here. Understood? So correspondingly, I must have a representation like this, x, y, z. Have you understood? So a point lying here will have a representation in 3D. That means this x will be one function of x1, y1. And this y will be another function of f2 of x1, y1. Understood? And this z will be f3 of x1, y1. So creating the additional axis require the creation of a new transformations. So I do not know how many of you are able to follow. I am saying the point is, if you don't have linear separability in the smaller dimensional space, you can get linear separability by projecting the points in a higher dimensional space. Have you understood that particular statement? Say yes or no?
Yes, sir.
Okay, so, but it is very easy. But creating a higher dimensional space requires the creation of so many functions. So suppose in the original data set, I have four features. That means my R is equal to 4. Suppose I would like to create a 15-dimensional higher dimensional space. I would like to create a new space consisting of 15 dimensions. Instead of 4 dimensions, I would like to go for 15 dimensions. So what happens now? I have to create 15 functions. One f1, one f2, one f3, etc. One f15. Each of them will be a function of these 4 variables. One f1 of x1, x2, x3, x4, f2 of x1, x2, x3, x4, f15 of x1, x2, x3, x4. So this many functions you have to create. If you want to create 15 axes, so the creation of an axis requires the identification of this f1, f2, etc., f15. Now it is humanly impossible. Because what type of transformation? See, if you have a look at that YouTube presentation, that fellow has given how he has created those transformations. Understood? I think somewhere here he would have given the transformations. If you have time, you can go through those comments. Understood? So, I'll repeat. Whatever I have told. Even if you have not understood anything so far, just listen to me these words. Support determinations is based on what is known as a function. So I would like to find a function f of x. I would like to find a function f of x. Understood? So I would like to find a function f of x like this, beta naught plus beta 1x. Understood? Now I know I have a solution for beta naught and beta 1. Let me not bore you by telling you where it is obtained by minimizing non-beta 1 square divided by 2, subject to all those conditions. Some nonsense you do and you get the solution. But the solution is acceptable only when we have linear separability. Only when we have linear separability, that solution will work well. That is one thing. Second, so okay. When you do not have linear separability, I said from a smaller space, you go to a very high dimension space. So there, if linear separability is absent here, you can achieve linear separability there. But the problem here is creation of a very high dimensional space requires that many transformations. Suppose you have 4 features here. if you like to have a representation of every point here in a 20-dimensional space, understood? So you need 20 transformations. F1 of those 4 variables, F2 of those 4 variables, F20 of those 4 variables. Who will give you those 20 transformations? Nobody can give you. So what we try to do now, understood, we simply make use of wherever we have. I have told you when I have shown you that when I showed you that solution, I said the role of your training data set comes where? Only here. I think it should be, it is somewhere here. Yeah, it comes only in the form of Xi transpose Xj. I said it comes only in the form of Xi transpose Xj. That's what I have told you. I think I have given here, somewhere here. 1 minute. Not here. Yeah. So where is my beta 1 hat? Yeah. Where is the token of hyperplane? 1 minute. Yeah. So this is what I wanted to tell you. So this is the place where you have this idea. So when you do not have linear separability, don't do anything. Understood? So you simply take your separating hyperplane, which is f hat of x as beta naught plus sigma alpha I hat. Plus sigma alpha I hat yi into x transpose xj. Understood? So I will take as my solution, I'll take this as a k of some x transpose gamma xj. Now you please listen. Here we have the original data. That means r dimensional data points. Now you have seen that from the r dimensional data space, you have moved to hr dimensional space. For example, if it is 4, it may be something like 20. So here you will have xj will be your 4-component vector. Instead of 4-component vector, you will have 20-component vectors. Understood? So what we have to do, I have seen that you have something like z1, z2, etc., z20. Understood? It's transpose. And z1, z2, etc., z20. So this is what you must be having. Understood? But remember, there is no need to go for the new transformations and replace this x transpose xj by something like z transpose zj, where this z is a 20-component vector and this is also a 20-component vector. We don't do anything. We simply borrow the idea of kernels. Understood? So here only kernels start entering the picture. Understood? So we'll be simply replacing x transpose xj by some function of x transpose xj. Understood? So this here you can use any kernel of your choice. Understood? The kernel is basically the function satisfying some very few properties which I have given in my presentation. Understood? So it has to be symmetric. It has to be symmetric and it has to be non-negative, and it will satisfy this Cauchy-Schwarz inequality. Understood? So here we have some example kernel functions. So this Gaussian kernel function is one of the popular kernel functions which are available, which is used in supported dimensions. Similarly, we have radial basis kernel function. Then we have polynomial. I think I cannot mention all this. Yeah, somewhere here I must have given. I think in my PowerPoint, because this is for a kind of a fast food service I do for my data science students. Understood? So because they will not have enough patience to learn, here I can show you some functions. So here we have a polynomial kernel, and here we have a Gaussian radial basis kernel. We have a sigmoid function. So many kernel functions are available there. Understood? So when we don't have linear separability, we simply make use of the kernel concept. Understood? So now you don't do anything explicitly, because manually you cannot solve all these problems. Like what I have done in the case of Bayesian, you can't do manually the calculations. Everything you have to heavily depend on your softwares. Understood? Now it is almost 3 o'clock. Don't say, because one problem with me is it's very difficult to stop teaching, but I would like to know, see, if at least one of you can summarize briefly what I have told in this 1 hour, I'll be the happiest person. I will have a small break after the summarization. I'll come back and I will try to help you how support taker classification is done with the help of your SK1. That is a different thing. Can any one of you summarize this, what I have told? But I do not know whether I have presented it carefully. If you have any doubt, or I want you to tell me. Can you tell me how to get, how to perform classification? Yes? Yes, yes, madam. Yes, madam.
In SVM algorithm, the main objective is to find the hyperplane that separates the support vectors for the target class. And there are two cases: linear separable and inseparable.
Okay.
If the case is linear separable, means we can use a function f of x is equal to beta naught plus beta 1 x. Here x is our training purpose, that is support vectors, and we have to find beta naught and beta 1. For that, we have to for separation we have to maximize 2 by beta 1, that formula.
Okay.
If the values of beta naught plus beta 1 x is greater than 1, means it belongs to the positive class, and less than or equal to means it belongs to the negative class.
Okay.
This is the case for separable. And if the case is inseparable, means then we can't do it using two-dimensional space.
Original dimensional space, or dimensional space. Yeah.
Yes, sir. So we have to project the points in a higher dimensional space. For that, the function we used will change to beta 1 plus summation alpha 1 y1 x transpose xj. For that, according to the number of dimensions, we can frame functions for each dimension, but it is not possible. So we are going to use the kernel concept, kernel functions. And the kernel functions are Gaussian, radial basis, polynomial, sigmoid. Using these functions, we can frame the...
we can manage this so even in the absence of a linear separability.
Yes.
So it is a nice summarization, because when somebody presents in 1 hour a matter which is supposed to be presented in 3 or 4 hours, if somebody can give back so much, I'm really happy. So basically, I'll quickly summarize. We would like to find beta naught plus beta 1 x. Understood? So this is your optimal separating hyperplane. So this is your hyperplane we are looking for. And I said for this beta 1 hat, you have a solution. For beta 1, you have a solution. For beta naught also, you have a solution. So once you substitute these solutions, you are going to get an expression like this. You are going to get like what she has told, an expression like this. Or what is that expression? So it is going to be beta naught plus 1 minute. I think I have very poor memory. That is why I keep on. So the idea is this one. So you go for beta naught hat plus sigma I ranging from 1 to n alpha I yi into x transpose xi. So this is what, or you can have j also. Nothing will go wrong. So this is going to be my f of x. So this is a function. This is the hyperplane which I can use for the see this beta naught substitutions gives this one. Understood? So now I am saying you go by this value. If it is greater than or equal to 1, put it in the positive class. Less than or equal to -1, put it in negative class. But the problem here is it will work very well as long as you have linear separability. When you do not have linear separability, instead of having x1, x2, etc., xr, these features, you have z1, z2, etc., zhr. So for example, for this 4, it can become to 50 or 40 or whatever it may be. Understood? So this inner product, so the product will be based on a 4 into 4 will become something like 50 into 50. But easy to tell. You can get z1, z2, etc., z50, but it is practically impossible. So what do? We go for a kind of compromisation. So we, without explicitly finding the transformations, we simply replace wherever we have x transpose xj in this expression, we simply replace it by some function of x comma xj. Some function of x comma xj we will be using. So this sum function and any function, the name of a function happens to be a kernel function. Any function which satisfies those non-negativity, symmetry, and the Cauchy-Schwarz inequality can be used here, and you can manage those so well. Understood? So this is what I wanted to tell you. Now, once we have come up to this, you have only two more things. I would like to spend. I do not know what he has done. I didn't have even time to discuss with that what he has done today morning. So now I am going to tell you how we can tune kernel. See, the choice of the kernel is going to matter. If you change the kernel, the performance of your support vector classifier will change. Not only that, in every kernel you have some parameters. See, for example, if you take the Gaussian kernel, you have one parameter. Understood? So you have gamma is one parameter. Similarly, in radial basis kernel, we have another parameter. So if you take the polynomial case, you have another parameter. So we have to make use of the training data set, and we have to see the classification validity measures, and we have to come out with the best classifier. That is one thing which I want to do. So has he done cross validation? Say yes or no, madam? One of you? Yes?
No, sir.
So when we come back, I'll tell you how to do cross validation to fine tune the parameters. That is one thing. Then I have to tell you how that support vector classification can be extended for. See, I said the entire discussion is for plus class and minus class. So when we have a multi-class problem, how do you manage? So there are two strategies. You see, unless you know this theory, you'll not be able to understand like what has happened in the case of navigation. Now, some of you must have seen for the first time in their life so much information hidden inside navigation. The same thing happens here also. So if you need a break, you'll have a break for about 7 minutes. We'll come back at 3:15 and try to learn as much as possible. I'll try to do as much as possible. As I have done today morning, I will share the notebooks with whoever is interested. So is it all right, or shall we stop the entire session today, wind up? I am willing to teach. It is up to you. You have to decide whether you would like to receive what I am going to tell or not. Understood? If you need a break, I am willing to give a break. Either, what do you say, madam? One of you, Young Mano Chitra, madam. I think தண்ணி குடிக்க போயிருப்பாங்கன்னு நினைக்கிறேன். நேற்று கூட என்ன சொன்னாங்க, அப்போ தண்ணி குடிக்க போயிருந்துச்சு. One more madam is there, Kalpana Devi. Who is there? Anybody is from the organizing committee? Shall we have a break or?
Sir, we have break, sir.
So, யார் பேசுறாங்க? வந்தனால?
Yes, sir.
No, sir. No, sir.
சரி மேடம், நம்ம வந்து ஒரு 3:15 வரலாமா பேக்?
Okay, sir.
I may need about a maximum 1 hour. Because demo கொடுத்துட்டு விட்டுறாங்க.
Okay, sir. Okay, sir.
ஆளை விடுற நான் போறேன் அப்படின்னு நம்ம இதோட மூடிக்காங்க பேசாம. Whatever you tell I will do. So வேணாம்னு சொன்னா ஃபோன் பண்ணி சொல்லிடுங்க, நான் நிறுத்திப்பேன். But I am willing to teach. Understood? Okay. But இது வந்து இப்போ பண்றது ரிப்பீட் ஆகிற மாதிரி இருக்குங்களா இல்ல கொஞ்சம் டிஃபரெண்டா இருக்கா?
Sir, யூனிக்கா தான் சார் இருக்கு.
ஓகே, சரி, நம்ம வந்து பேசிக்கலாம்.
Thank you, sir. Dear scholars and faculty members, please take a 15 minutes for break. Then after you can join this same link. சொல்லுங்க. இல்ல 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 வந்தனாவா வேற யாருன்னு கேட்டாரு. இல்ல வந்தனாங்க. ஏன்னா என் பேர் அவருக்கு தெரியாது. ஆமாம், அதுக்குள்ளே வந்து நான் எஸ் சார் என் பேரை கேட்டா அவருக்கு கொலவே பரவாயில்ல அவர் என்ன நினைப்பாரு. என் பேர் கேட்டாலே அவருக்கு அவ்வளோ ஆனந்தமாக
ஒரு காலத்தில் ஆர்கனைசராக மனம் பண்ணுறாங்க. அதை எப்படி வாயில சொல்லுவாங்க சொல்லாது. இப்படி மேடம் அந்த எப்படி நடந்ததுக்கு எந்த எப்படி போனாலும் நடத்துறாங்க. எங்கேயோ போகிறீங்க
இங்க முடிச்சோன்னு மெயில் அனுப்பிச்சிருக்கேன். அங்க போய் அதை ஓபன் பண்ணி சேவ் பண்ணி அப்புறம் அங்க முடிச்சோன்னா இல்லைம்மா இந்த பாருங்க டைல எழுதியிருந்தது வச்சுட்டே
Okay. Shall we start? Madam, start பண்ணிடலாங்களா?
சார் யாரும் ஆன்சர் பண்ண மாட்டேங்கிறாங்க சார். 2 minutes வெயிட் பண்ணுங்க சார்.
Okay. Okay.
Okay sir, we will start sir.
We'll start. Now,
Sir, we will
Yes,
start
madam.
sir.
yeah. Now, let us begin. So before I get into the practical work, I want you to understand how multi-class classification is taken care by your supported commissions. Understood? Yeah. Can you hear me?
Yes sir.
Okay. So what I am trying to tell you now, please listen. You have to see. You think of one small problem, like what we had in that Egyptian skull data. We had Egyptian skull data. How many classes we had there? If I remember correctly, you had 5 classes. Am I right?
Yes, sir.
Okay. So we had 5 classes. So now let us see how SPM can be utilized for performing a multi-class classification problem. Please listen. You can ask me, all the software it is giving the answer, why do you bother all those things? But really it matters. See, there are 2 approaches to deal with the multi-class classification problem. One is 1 versus 1. One is 1 versus 1, and the other strategy is 1 versus many. Understood? So 1 versus 1 and 1 versus many are 1 versus the rest. Understood? Yeah. 1 versus rest is okay. So written as 1 versus many. Understood? So now what I will be doing now? Now you divide a K class problem into K binary class sub-problems. Understood? See, for example, you assume that you have, for example, if you have some time periods like minus 4,000, I don't remember exactly, minus 3,000, minus 300, and you have something like 500 and 1,000, whatever it may be. Now what I will be doing now, since I have 5 classes, I will create 5 sub-problems. I will create 5 sub-problems. Understood? So this minus 4,500 will be taken as the positive class, and the remaining will be taken as the negative class. So similarly, minus 3,000 will be taken as the positive class, and the rest will be taken as the negative class. So positive, negative, and positive, negative. Can you follow this? Please say yes or no.
Yes, sir.
This is what I have explained here. Corresponding to, so you divide the K class problem into K binary class subproblems of the type Kth class versus not the Kth class. Now, corresponding to the Kth subproblem, you construct a classifier, like what we have done in the case of supported commissions. Understood? Now, you calculate your value of your Fk hat of x. Understood? So you have to calculate for every such value. See, for example, suppose I have some training data set. So I have some set of 4 values. I think we had 4 features. Understood? So you substitute those 4 features in the first function. So you will have one f1 hat. So you have to substitute it here. Understood? So you find the value of your f1 hat here. Similarly, you will find the value of f2 hat here. Value of your f2 hat here. The value of f3 hat will come here. f4 hat will come there. f5 hat will come there. Now you have to see among these 5 values, which value happens to be the maximum. Now we will be assigning that particular object into that particular class for which that hyperplane assumes the maximum value. Have you understood? Say yes or no. It may not be very clear. I will tell you why it will not be very clear. Now you can ask me from where you have those functions. See, here I have f hat of x happens to be my beta naught hat plus sigma alpha I hat yi x transpose xi. So this is my function where I have only two classes. Some of them belong to the positive class and some of them will belong to the negative class. Am I right?
Yes,
Say yes or no. So when I consider the first subproblem, 30, see we had totally 150 instances in the data set. 30 of them will belong to the positive class. That means you will have yi. Only in 30 cases you will have yi. And in the remaining 120 cases, what will be your yi will be? Yi will become -1. So this yi will become, see this yi will become plus 1 in 30 cases, and it will become -1 in the remaining 120 cases. Understood? Correspond. So this value will change. So the first 30 yi's will become +1 and the remaining 120 will become -1. Now, so that is how we are going to get the first function. Now when I consider the second function, first 30 will be negative, the second 30 will be positive, and the remaining 90 will be negative. Can you follow? Say yes or no?
Yes, sir.
Okay, so that means you are going to have different functions. So now when you are given, so that means you have how many functions? You have 5 functions. F1, F2, F3, F4, F5. Because yi's are changing. So the functions are changing. So what I will be doing now, I will be considering these values. Suppose the value of my F1 value happens to be 4.3. My F2 value happens to be -0.4. And F3 value happens to be 1.2. F4 value happens to be 5.2. And F5 value happens to be 0.8. Then immediately what I will do? Because this value is maximum, I will be assigning that to test object to this 4th class. That means I will declare that belongs to the period 500. So this is what we do in one versus rest. I hope it is clear. You do not know. Is it clear or not? Say yes or no. Okay. So this is how we do one versus rest. Now what do we do in 1 versus 1? In 1 versus 1, see when we have a k-class classification problem, we had k subproblems in 1 versus rest approach. When we consider 1 versus 1, we'll be having KC2 problems. We'll be having, see, suppose you have 5 classes, like what has happened in the Egyptian skull data, you have 5 C2 classes. 5 C2, that means what? 10 problems you'll be considering. You'll be considering 10 problems. Understood? So, for example, period 1, period 2, period 1, period 3, period 1, period 4, period 1, period 5, like that you'll be having 10 such pairs. Understood? So, this is what he says. Now, corresponding to each pair, you have to construct a classifier. The classifier FJKX is constructed on coding the jth class is positive and the kth class is negative. So, that means what? You'll be having this as the positive class and this is the negative class. So here P1 is positive class, P2 is negative class. P1 is positive, somewhere here I will be having P4 and P5. Understood? So P4 will become positive class and P5 will become negative class. So I will be having 10 such problems. Now what I am going to do with those 10 such problems? Then you consider, then for when a test object comes, you aggregate the votes for each class. You have to aggregate the votes for each class. That means you see in how many cases you have plus and in how many cases you have minus. Then you have to consider, now can you follow or not? Please listen. Have you understood? Say yes or no, madam.
No, sir. Can you repeat, sir?
Yeah, I will repeat. We have to be very honest in the learning process. It is a good symptom that you want. See, I have 1 versus 2, 1 versus 3, 1 versus 4. Let us not go in a hurry. 1 versus 5, 1 versus 6, 2 versus 3, 2 versus 3, 2 versus 4, 2 versus 5, 3 versus 4, 3 versus 5. and 4 versus 5. So I have how many first problem, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. Okay, so I have 10 problems. Now, what I am going to do now, I will be considering the number of cases. So I will consider the votes. This is what I have explained here. Then, when a new object comes, we have to calculate all the 10 values. I have to calculate this value, this value, this value, all the 10 values I have to calculate. Now, when I calculate like this, I will see in how many cases I classify that object into 1. See, for example, suppose here it becomes 1, and here it becomes 3, and here it becomes 1, and here it becomes 3, and here it becomes 4, and here it becomes 2, here it becomes 5, and here it becomes 3, and here it becomes 3, and here it becomes 4. Okay, so when I use that function, it is going to first class. When I use this, it is going to my first class, third class, fourth class, first class, third class, second class, fifth class, third class, fourth class. Okay, now that object, in how many cases you have 1? In how many cases you have 1? You have 1, 2 cases. In how many cases you have 2? You have 1. In how many cases you have 3? In how many cases you have 3? No.
3 cases.
4 cases we have. Understood? In how many cases we have 4? No cases. No, here we have 1. 2 cases. In how many cases we have 5?
1.
Only 1. When you total, it must become 10. 70. So now this 3 has received the maximum vote. Therefore, the test object will be assigned to the 4th class. The test object will be assigned to the 3rd class. And if only this is your class, and these are your votes. So the votes is secured by the class 3 happens to be the maximum, namely 4. Therefore, the particular object will go to that class. Have you understood? Yes or no?
Yes, sir.
Okay. So this is how SVM performs classification when we have your two multi-class situation. Okay. Now let us see. I do not know. So let me just proceed with this. Let us continue with our work. Now let me give you some demo. Understood? I don't want to permit you to think like how to start now. So I don't want you to try along with me. I just listen to me. I will share the notebook with you. You can later on you can try. Understood? Okay. First, let me show you how we can perform classification. Understood? Then I will tell you how we can go for tuning if time permits. Understood? Okay. Now let me. This system is somewhat slow. It will take some time. Yeah. We must have started the system a little earlier. Anyway. Yes. I think it is research. Select starting. So, yeah. Okay. So let me just give one small demo. Just a minute. Okay. Fine. Now let me start with the new workbook. Now I would like to just make use of the same Egyptian style data. I think yesterday we had I could have continued with that itself. Anyway, let us not change our ideas. So what I would like to do now, first let me take my, I would like to import my data set. Okay, I think if I proceed with that, I'll be able to do fast. Open yesterday's notebook I'll use. I don't want to type again and again. So I think navigation FDP. Here I go. So, yeah, so let me just, if I change this, see, let it go there. It's quite simple. Okay, don't get panic. I'm not going to hold you beyond 4 o'clock. So, profiling I don't want. So, just I would like to read my data and let me just confirm whether the reading is taking place correctly. Okay, so now it is reading. Okay, so it is read. Now what I'm going to do now, I'll be separating like what I have done in the case of navigation. Here also I would like to separate my target and data. So let me take access this and this was this one. Okay, so now let me just run this, we see what happens. So I am running this. So I have run this, so it is over. So now we have separated these two things clearly. Now what I'm going to do now, just let me come out with a model like this. So I'll have one model like this. Model happens to be, I have to import my SPA function. Understood? So towards that, I'm going to from sklearn dot from sklearn import. I will import only SPM. From sklearn, I will like to import my SPM. Yes, I think it has come out well. So now let me go for my model. So I would like to have my model like this. So model happens to be SPM dot SPM.svc. I am not going to do anything more than this. Okay, so let me run this. Let me see whether the model is correct. So here I have created the support determination, but now I am going to associate my data with this one. So how I am going to do that one? Now I am going to fit my model like this. Understood? Yeah, 1 minute. So I am going to fit my model as a model dot fit of model dot fit. Morning you have done these practicals, no? Am I right? Model fit of x comma y. Understood? So let me just see whether it's working out well. It's running. Let us see. Model dot fit of x comma y. I think there is a so this warning you can just ignore. Understood? So here I have run this using a default. So it has completed the fitting of the model. So you don't worry about that warning. So it is completed the process of fitting the model. Now what I can do now, I can see here, if I want, I can go for the prediction. So what I will do now is just go for a model dot predict of x. So when I call model dot predict of x, I'm going to get the value like this. Understood? So these are my predicted classes. I hope you can understand. Can you follow? Say yes or no.
Yes, sir.
Okay. Now yesterday we have done the same thing for the name version. Now let us just have a quick comparison of what has happened in the case of name version with this one. Understood? So now we will be surprised why this fellow is working so well. Now I'll go to my, I do not know which page is that, this I will close. Now let me come to this. So let me just put it here. And there I have taken. So I would like to get all the scores. So here I have used y, but here I have used model. I'll use model dot predict. So I think I used CLF here. Model dot predict. So let me go for model dot predict. Understood? So let me go for model dot predict. So I'll go for model. Okay. So let us see what happens. Yeah. Are you not surprised? What was the finding yesterday? It was very poor. Understood, no? We had something like 36%, 38%, 36%, etc., etc. Whereas this fellow support recognition is doing wonders. So it is almost giving 100% accuracy. Am I right? Say yes or no.
Yes,
So
sir.
this is the beauty of support recognitions. That is why I used to tell support recognition will normally beat other classifiers. In fact, sometimes it will beat even logistic regression also. Understood? So this is the power of support recognition. Now you can ask me, you said so many things about the kernel, you said so many things about one versus many, etc. Where all the things have gone. Understood? So here I want you to have a look at this. See here, we have so many things, but I want you to go through this particular part. So the decision function shape is an OVR. Can you read that part? Can one of you read? Say yes or no. Decision function shape is OVR. That means for the multi-class situation, we are using the strategy of one versus rest. So the one versus rest gives you this answer. Now if you change that as a 1 versus 1, you are likely to get some other answer also. One more thing I would like to tell you. You can ask me, what happened to my kernel? So the kernel by default is using the radial basis kernel. So the radial basis function is used for addressing the issue of the absence of linear separability. If you want, you can change instead of a radial basis kernel, because you have come out with one, you can be very happy. Understood? But remember, what has happened now? You have used some data set for the purpose of training, and the same data set you are using for the purpose of testing also. So it is not a fair game. Understood? So you should know how to create data sets for the purpose of doing cross-validation. I do not know whether you are able to follow or not. Can all of you follow? See?
Yes, sir.
Now, suppose, see, instead of taking all the values, now let me take randomly some values from this. Let me see what happens. Probably it may also work out well. Now, what we normally used to do now, we will be, whenever we want to do a cross-validation like this, we will be dividing the data set into two parts. One part will be used for the training, and one part will be used for the purpose of testing. Please feel free. Are you able to follow what I talk? Say yes or no.
Yes, sir.
Okay, so what I am saying now, see, in the data set I had 150 objects. I have used the entire 150 objects for the purpose of training, and I used the same 150 objects for the purpose of testing also. So it is not surprising to get the answer 111. It was not happening in the case of neighbors. So now what you can do now? You can divide this 150, some for randomly you can keep for training. You train the data set, you use one part of the data set for the purpose of training, and one part you use for the purpose of testing. So now I am going to tell you how we can perform this kind of exercise. So, and at the same time, you can study what can I say, parameters choosing also you can do beautifully. That is what I am going to tell you. Now first let me tell you, please remind me, I will send you one notebook which I have used for our students, machine learning students in the data science program. Understood? So now what we do know, for selecting the model, we will be there from sklearn dot model selection. From sklearn dot model selection, from sklearn dot model selection, I would like to import one component called train underscore test underscore split. So I'm sorry, my sound shoes. Okay, so now I'm going to use this particular component for the purpose of dividing randomly the data set into train and test. So that is the main role of a train underscore test underscore split. Now you can ask me how we can get the results out of it. So what we do, we create two portions. One is for X train. So I will give you four components. One will be X train, the other will be X test. Similarly, I will be getting while train I will be getting, comma, y test. Those who are familiar with Python will know what I'm trying to do. So that function will create, we can return four different items. One is train underscore test underscore split. Train underscore test underscore split. Now we have that x, we have that y, comma. Now we have to decide what has to be your test size. So test size will be a number lying between 0 and 1. For example, if you give 0.5, it will use 50-50 ratio. See, here it will use 50% and here it will use 50%. Suppose you want majority of them for training and the rest of them for testing, you can give 70-30. That is your choice. So, for example, I can have the ratio test size is 0.70. No, test size 0.70 means for training you'll be using 30%. Let me put it like this. Test size 30. Understood? Then if you want to create, if you want to compare the results at a later point of time, you can go for a random state. So if you do not want to have any deterministic sample, you can avoid this. This is purely optional. Understood? Even test size is also optional. So it is executed. Now, if you have a look at your x dot shape, it is going to be, x dot shape is going to be, x dot shape is going to be 150, 4, because in the given data set we have 150 instances. Now if I ask my x underscore train shape, can any one of you predict what will happen? X underscore train shape, it will be 70% of 150. 70% of 150 is what? 105. Can you follow? Say yes or no?
Yes, sir. Yes, sir.
Because I have used 30% for test. So on the other hand, suppose I have used something like 50%. You can see here, now it will change. So it will become 150, you will have 75.4. So it is always better to keep the major portion for training and the remaining for testing. Now this will be more credible. See, don't be happy by looking at that accuracy 1, precision 1, recall 1, entropy 1. Understood? I think how many are there left in the meeting? Am I talking only with one student? How many are there? Only 33. Okay, no problem. So that is why I said Dr. Parthiban, I am not very keen to ask. Even somebody wants, you'll be happy. Understood? Anyway, let us not talk nonsense in their opinion. Where is my notebook? It is here. So I have come up to this. So I have come up to this. Now what I would like to do now, I would like to have my parameters. So if I want, I can decide my kernel, I can decide my parameters in the kernel, all those things I can do, and let me just try what are the parameters which we are going to do. So tune the parameters. So let me have, so first let me try tune the parameters. So here I will be giving a list. So this is a list consisting of, what can I say, dictionaries. So here I have one part happens to be my kernel. Let me make the font size slightly bigger. I'm not able to see correctly. So kernel is your key, and the values happen to be, let me take radial basis, RBF. RBF is for radial basis kernel. Then I can have one more this thing. So I can have gamma. So I would like to have in the radial basis kernel we had a gamma parameter. So let me have for gamma. Gamma, I am assigning the value of 1 e minus 3, 1 e minus 4. Just only one kernel I would like to try. Because, let me just check whether the parameters are properly tuned. Yeah. So I think it has come out. Let me check whether it is waiting for something else. Parameters. So it goes like that. Parameters. Okay, tune the parameters. So it goes, what's this? Tune parameters. Here I missed. There I have learned and okay, fine. So I am just checking what happens when we have two values for gamma. Understood? So now what I will be doing, so this is my basic. Now I would like to perform a kind of cross-validation. For example, if you want, you can have one more choice also. For example, if we have, in addition to this kernel, let me have one more kernel also. Let me have kernel, I'll have linear kernel. Let me have kernel. I would like to have just linear. So the linear is one kernel. Colon with the list linear. So linear is the kernel which I want to have. Understood? So I think this is enough for me. Let it take the default values. Let me just run this and check whether there is any free from any mistakes. Yeah. So it has come out like this. Now, what I can do now, I can go for what is known as a grid search. Understood? So when I call my grid search, I'll be able to get beautifully the answers. So the results, I'll call this as results. So results happens to be, or I'll call this a CLF. Classifier happens to be grid search cross-validation. So it will search for the best set of parameters. Grid search, which one I am trying to tune to support a classifier, and tuned parameters. Let me just, I think I included this particular library there. I have included, let me include here itself. So for grid search, I have to include one more library. Understood? So I would like to have from sklearn dot model underscore selection import grid search CV. Grid search CV means the CV stands for cross validation, so it is doing grid-wise. That means it will take all possible combinations which we have given there. First, let me run this. Otherwise, it will create the give error. So let me run this. Let it go there. Yeah, so it is gone there. Now let me check whether it is free from errors. So SVC is not defined now. Why? Support a classifier I have defined now. So from a scale under let me have SVC. Have SVC. How it worked there? I don't know. Okay. Cannot import an SPCR. From sklearn.svm. From sklearn.svm. Okay. So model equal to this one. So it is gone. Okay. So let it go like that. So let it come here. So when I run this, so here why this error comes? Can anyone of you identify? So here I will be having grid search CV, SVC tuned parameters. Grid search CV, SVC is not defined. Why? It has to come. SVC I have defined now. From sklearn.svm import SVC. Probably in your system it should work because I had a problem. Has it work? Okay. Can you follow? Say yes or no? Okay. So now I have to fit. So I will be fitting this using clf.fit or clf.fit. I will be fitting using train. X underscore train comma Y underscore train. This I will be fitting. So let me run this. Let us see what happens. Yeah, so I can have. Then I will have a 4 set of values. So when I run this, it goes like that, it goes like that. Now when I execute this, I am getting 0.01 as the best answer. Understood? So like this, you will be able to get what are the best parameters, and also you will be able to get what you can say, your classification report also you can get. So the classification report you can get just by calling Y underscore true, y underscore true, comma, y underscore true, comma, y underscore test. I will be calling this as y underscore test. I hope you can understand. So true value happens to be y underscore predictor. So here the true value happens to be whatever you have in the test set. Okay. Y underscore test, comma, CLF dot predict of x underscore test. I hope you can understand. Please try to follow this particular part. I am almost nearing the conclusion. See what I am trying to do now. I am predicting the classes of the objects which are in the test class. Understood? So that I am placing here. And my y true happens to be whatever I have used for y test. I hope you can understand. Can you follow? Say yes or no. Yes? Are you there?
No, sir.
Yeah.
What?
I will tell you one small thing. See here, when you have completed this particular part, you have identified the best particular choices. Now what you are going to do now, all those things were done only with the help of the training data set. Am I correct? See here I have used only the training data set. X train, Y train. Am I right?
Yes, sir.
So now the trained classifier I am going to use for assessment with the help of the test data set. So for the prediction purpose, I will be using the test data set. So I will use the same classifier and I will predict the classes of the objects which are there in the test class. Understood? So whatever is written here, so this y underscore test will become y underscore true. Am I correct? See, X test is the portion which you are using for the purpose of testing. So it will have some target classes. Am I right?
Yes, sir. Yes, sir.
So that is going to be what? Where y underscore test. So that y underscore test I am using as it is not necessary to define like that. I could have used straight away used y underscore predict and perform that one. See, I think I am unnecessarily confusing you. Let me put it like this. Y underscore predict. This is the usual style of doing. I hope now you can understand. Am I right?
Yes.
If you run this, let us see what happens. So I have predicted. Now what I am going to do now, I am going to predict my classification report. So when I go for my classification report, this I have report, classification report of what I have to do. First I have to do y underscore test. Yeah, that is the actual true value. So to avoid the confusion only I have renamed like that. And here I have y underscore predictor. So this will not work because I have not imported metrics from sklearn dot metrics metrics from sklearn dot metrics import classification underscore report. Understood. So let me run this. Let us see what happens. So it is done. Can you follow? Say yes or no.
Yes, sir. Yes, sir.
This is the actual problem. Now you please listen. Here you had 1, 1, 1, 1 and all. So you had that much happiness. But when you use this kind of split, the performance becomes miserably bad. Now why? One reason which I can tell you is because we have controlled the gamma values in this manner. 0.1, 0.01, 0.00, 1.00. But by default, it was giving some value for gamma. I think it was given for gamma some value here. I don't remember. Can you just, for gamma it was, it was used not this one, Gaussian, radial basis, but here the degree is taken, a coefficient degree. Where is gamma? Definitely it will matter. Definitely it will matter. For example, it matter in so many ways. Now let me just check. Instead of a test size 50, let me take 30%, or I will take only 10%. I would like to use majority for training. So let us let me run this. Now you are going to see things will change. 100% will change. No doubt about it. Now we can see here. That's totally changed. Can you follow?
Yes, sir. Yes, sir.
So it is changing. Understood? But still, this is one thing which we have to understand. See, this precision is a 0.11 and the recall is 1, but the reference score is very poor. But still, it is not very encouraging. But it changes. It changes. Have you understood? Okay. Now, if you want, you can redeem this.
Past 3 days.
Like what I have done with the case of Libya. Now let us see what happens. If it takes that deepest secret value, not a trained value, we give a better result. No, it's not strictly.
இது மட்டும் எழுதுறீங்களா?
I have gone here. Understood. So here we are giving in a hurry so many ill-defined values. So this is not at all encouraged. Understood? So everything depends on what you are trying to give here. Understood? So most of the times it is better to go with the default setting because this kind of thing will make use of some hidden algorithms which will give you very good results. Understood? Okay? Do you have any other doubts?
No.
In fact, to be frank, I was sleeping. Fortunately, I didn't put my mobile in silence. If I have put in silence, that's all I have given here. Suppose we have only one data set. When something comes, you have to see whether it is in line with what is available in given data set. If it belongs to the class, then it becomes an unusual item. If it is not a member of that one, it will become a novel item. This we use in intrusion detection and all. Okay, so I have decided to stop with this. If you have any specific queries, feel free to ask. Yes, anyone can ask. Dolphin madam, are you there? She will not be there. She is there.
Hello, sir.
Sir, poduma sir.
Sir, உங்களுடைய கன்வீனியன்ட் தான் சார்.
போதும் சார், நம்ம திடீர்னு ஆரம்பிச்சோம். அவங்களும் போதும் பரிதாபமா உட்கார்ந்துருக்காங்க. நான் பண்ண பார்த்துட்டீங்க.
Thank you so much.
Thank you,
I
sir.
have heard with him. It is not a good practice to agree and suddenly abscond. நல்லா இல்ல இது அவர் பண்ணது.
பரவாயில்ல ப்ரோ சார்.
Okay sir, okay sir.
Can I
Thank you so
continue,
much.
sir?
Yes madam.
Sir, I really heartily thank to our resource person.
Okay madam.
Sir?
Yes madam.
I heartily thank to our resource person, Dr. Sambat sir, who spared time from his busy schedule to make this FDP in great success.
Not a busy schedule madam. I was just sleeping. Suddenly I got a call. That's all. Okay madam.
From past 3 days, we traveled along with you and gathered the knowledge which gives us to initiate our progress towards data science and machine learning. Thank you, sir.
Thank you madam. Thank you.
Bro sir, tomorrow
there sir. Okay.
Bro sir, tomorrow also you should join.
Again. நான் நடுவுல வந்து
மேடம் இன்னைக்கு தேங்க் பண்ணாங்கல்ல உங்களுக்கு.
ஆமா சார்.
அதனால சொல்றேன்.
ஓகே சும்மா வரேன் சார்.
நாளைக்கு FTP இருக்கு, நாளை மறுநாள் இருக்கு.
ஏன்னா நீங்க கூப்பிட்டப்போ எனக்கு வேற ஒரு ஐடியா இருந்தது. நாளைக்கு அவர் சார் ரெட்ஜ் ரெக்ரெஷன் எடுக்க போறப்போ சில கான்செப்ட்ஸ் எல்லாம் ரெஃபர் பண்ணுவார் ரெக்ரெஷன் மாடல்ல. இந்த மல்டிபிளிங்காரிட்டி அதெல்லாம் எப்படி ஹேண்டில் பண்றதுன்னு சொல்லிட்டு அது போனால் நல்லா இருக்கும். அவருக்கு இஸ் ஆல்சோ இன் எக்ஸ்பீரியன்ஸ் பர்சன். ஐ வாண்டட் டு டெல் தட் ஒன், பட் தட் வுட் ஹேவ் பீன் மச் மோர் அப்ஸ்ட்ராக்ட். இன்னும் ரொம்ப அப்ஸ்ட்ராக்டா இருக்கும். அது வந்து சில மேட்ரிக்ஸ் ஐடியாக்கெல்லாம் நம்ம யூஸ் பண்ண வேண்டியிருக்குங்க. அதனால காலையில அவர் என்ன பண்ணாரோ அதுக்கு ரிலேட்டடா பண்ணி விட்டாங்க. அதெல்லாம் வேற பண்ண இவ்வளவு தூரம் யூஸ்ஃபுல்லா இருந்தது தெரியும்.